So our one learning intention to explore the unit circle in the context of circular functions and to derive this measurement system called radians. So I'll just drop that over here. Okay. And we're going to define radians and how we convert between radians and degrees. But first of all, we need to figure out what they actually are. So, let's define radians with the unit circle. So what do we mean when we say a unit circle? Does anybody know?
A circle with a radius of 1.
A circle with a radius of 1. So if we have a radius of 1 here, then what is this coordinate here?
1,
Not 1, 1. So
One.
here,
0,
1 across and 0 up. 1, 0. The coordinate here is
0,
0, 1. And the far left, -1, 0. And down here, 0, -1. Okay. So the unit circle, as we sweep around the edge here, the radius of length 1 sweeps out a circle like so. Now, what can we say about the circumference of this unit circle? What do we know about the circumference of a circle?
It's given by 2 pi r.
Okay, so the circumference is given by 2 times pi times r. But for the unit circle, we have the special condition where r is always 1. So the circumference is equal to 2 times pi. Now how does that help us as opposed to degrees? Well, what we're going to have is a measuring system which is always 100% accurate. We don't have decimal places, we're not using irrational numbers. What we're using is a fraction of its exact, let's just say position. So if we unraveled this circumference here and just put it in a line, we have at the start 0, and what's the full, if I walk to the end of the line, how far have I walked? 2 pi. So what we can say is, if the angle is pointing directly up at 90 degrees, then this is a quarter of the way through 2 pi. If the angle is 180 degrees, it is half of the way through 2 pi. If the angle is 270 degrees down to 0, -1,
That's 180.
pardon?
Isn't that 180?
So 90, 90, 180, 270. So we can use degrees to figure out where we're pointing in terms of an angle. But this, in our new measuring system, we're defining a distance around here, or an arc length, which corresponds with the angle. So here, 90 degrees, 180, 3 pi on 2, so 1.5 times pi, and then 2 pi, we're going to use these as reference points. So, if this position here can be said to be a full length of 2 pi, then half of that here is half of 2 pi, or simplified, just pi. Half of pi, so an angle that doesn't stretch all the way to 180 but just goes to 90, could be said to be how far around to pi? From here to here. Half of pi, pi over 2. And if we, because as in convention, a positive angle in degrees is rotating anti-clockwise, so keeping that same convention, if we have an angle that stretches all the way to 270 degrees, how can we write that in terms of pi?
100 pi over 2.
3 pi over 2. These are just numbers. So what we've defined here is a measuring system, which we refer to as radians, where have I written it here? Okay. 1 radian 1, and we define radians as a little c instead of the little circle for degrees, is defined as the angle subtended at the center of the circle by an arc length of 1 unit. So from here to here is 2 pi. Pi is 3.14, so what is 2 times that? 6 point. Yeah, so from here all the way around one circle is 6.2 and on and on and on radians. So what we have, because we circles have this relationship with pi, we can define this measuring system using radians, which we can then have the exact angle. Okay, so what have we just summarized? You've got this in your book, and in your notes, and this is just a quick snapshot of quite a lot of the commonly used angles. So 0 degrees, 0 radians, or 360 degrees and 2 pi radians. 90 degrees, pi on 2. 180 degrees, pi. 270 degrees, 3 pi on 2. And then we have the parts in between. If we break 90 up into thirds, then we have 30, or pi, a third of pi on 2, pi on 6. So this angle here from 0 to 30 degrees, if we were representing this in radians instead of degrees, then we could say that this angle is equal to pi over 6. Why? Because it points to the position which is pi on 6 of the way throughout the circumference of a maximum of 2 pi. Do I have any questions about defining the radians? Where do those numbers come from? Let's pause for a moment. The extra part of the information around the outside, we're not going to use immediately, but it will be handy for you to have. These are the coordinates around the unit circle. And for some people who have started specialist, you might have seen these before. So that's just saying that this coordinate here is at root 3 over 2, comma, with a y coordinate of a half. So we will be referring to this when we get into some of the solving for circular functions. So now that we've defined this measuring system, what's a quick way to be able to convert between the two, between degrees and between radians? Since pi radians is equivalent to 180, just like 2 pi is equivalent to 360, we've just simplified it by dividing both by 2, then we can convert between the two by this conversion factor, 180 over pi, or pi over 180, depending on which one we're converting to. A really handy way to think about it is that our radians, we always want to have in terms of pi. And our degrees, we don't want any pi in there. We just want to have in terms of degrees. So, when we're thinking about the conversion factor, if we're converting 60 degrees into radians, we want that now to have a pi in there. So we're multiplying by the factor which has a pi at the top. So let's just step through A together. Simplify the following. Convert 60 degrees into radians. Well, we've got the conversion factor 180 over pi, or pi over 180. We know that in radians we want to have pi as part of the term. So we're going to multiply by the one which has pi in the numerator. So pi over 180. 60 times pi over 180. We can simplify 60 over 180 as 1 over 3. So 60 degrees is the same as pi over 3 radians. When we already have it in terms of pi, we typically don't use the little c. So with the second example, convert pi over 6 to degrees, once again, we look back to our conversion factor. We're trying to remove pi so that we just have it in terms of a number in degrees. So this time, we're going to multiply by 180 over pi. Pi over 6 times 180 over pi. The pi's cancel out. And 180 divided by 6, 30. And we've got our little degree symbol there. We've missed out on a bit of the text here. It should say convert 13 pi over 6 to degrees. Okay, which conversion factor should we use?
Radius of degrees, so times 185.
Times 180 over pi. So it's already got pi in it. 13 pi over 6 times 180 over pi. Now, we're doing this in part in section A of the test and we don't have access to a calculator. So let's just simplify it just piece by piece. What would be the most obvious thing we could simplify there?
6 and 180.
Pardon? Well, 6 and 180, that would be my second go-to, and the 2 pi's. So they're the two things we're going to, first of all, let's cancel out the 2 pi's. And then the 6 and 180 becomes
1 and 30.
1 and 30. So it leaves behind 13 times 30. 10 times 30, 300, 3 times 30, 90, 390. Okay. And that's our introduction for radians, where they come from, and how to convert between radians and degrees.
Would it just be 30 degrees?
Pardon?
390 is more than 360, so we've got around more than once.
Yes, but we're not looking at the we're not saying what is an equivalent in a certain quadrant, which is what we will be looking at shortly. What this is essentially saying is that something has occurred which is swept around more than a full period, but in terms of symmetry properties, we'll be looking at those on Friday.